Okay, I think we can make a start. Hi everyone, welcome to the London Machine Learning Meetup. We are going to have a talk today by Mingxing Tan, who's from Google Brain, who's going to be talking about AutoML for efficient vision learning. Mingxing is going to talk for about 40 minutes, and then we're going to have some questions. So please put your questions into the QA during the talk, and then when it comes to the questions of the QA section, we're going to ask you to raise your hand if you want to ask your question yourself. Otherwise, we're just going to read your question out for you. The QA will be moderated by myself, Giuseppe, and Alessio, who are my colleagues from Evolution AI. Evolution AI is also the meetup. For right now, I think that's all we need to know. So I'm going to hand over to Mingxing. Thanks, Mingxing.
Thank you, Martin, for the introduction. Hello, everyone. My name is Mingxing Tan. Currently I'm a researcher at Google Brain. It's my pleasure to be here and have a discussion with everyone about AutoML for efficient vision learning. So everybody knows deep learning is taking off, and it's largely for three factors: because we have more data, we have more compute, and we have better deep learning algorithms. However, designing deep learning model is very difficult. For example, for convolutional neural network for computer vision, in the past, we have designed tons of different neural networks from the early, like LearnNet, AlexNet, like Inception, ResNet, DenseNet, SENet, and so on. So if you look at all this neural network architecture, you will find they are kind of similar, but they are also very different. They are similar because they're all convolutional neural networks. So you can see there are some convolutional layers, and then they have multiple layers, and to taking an input image and downsample to the final classification head. However, they're also very different. For example, if you look at the ResNet, it's a very standard linear structure, but for Inception, you will see there are many branches. So there are always some different trade-offs for different design principles and philosophies. And as humans, we have spent tons of time and efforts to make these neural networks better. So the question is, what should be the next generation neural networks? Can we automate this very expensive design process? So we call it AutoML, right? We want to automate all the things. Well, so what is exactly AutoML? Well, this AutoML concept is very broad, but in general, it means maybe we can leverage a lot of compute to automate some of the work in collecting data or designing neural networks. In terms of data, my colleagues designed some algorithm like auto augmentation, or there are also some recent work on self-training and self-supervised training. In terms of neural architecture design, our goal is to leverage a lot of compute to design better neural architectures or better neural architecture design choices. So in this talk, I mainly focus on neural architecture search, which means we use a lot of compute to design better neural architecture. To give you a sense what kind of progress we have made in the past 3 or 4 years for AutoML, especially for neural architecture search, in this figure, we show 3 curves. The bottom curve is a hand-designed neural networks, including ResNet, DenseNet, SENet, and all these famous hand-designed networks. In the middle is first-generation AutoML models. We call it NASNet and AmoebaNet. There are also some other models. In the latest, in 2019, we also designed another network called EfficientNet. If you compare these 3 curves, you will find AutoML design models, they're much more efficient in terms of accuracy and flops trade-offs. And especially the latest EfficientNet, it has much less flops and parameters, but pretty good accuracy. So the question is, how do we get here? Well, it mainly includes 2 main steps. The first step is we leverage neural architecture search to find a good candidate, a relatively compact model. And the second step is based on this compact model, we come out some way, automated scaling way to scale up those models to achieve better trade-off between accuracy and flops. So in this talk, I mainly cover these two parts: how to find a good compact model using neural architecture search, and how to scale up your model. Okay, let's go to the first part, platform-aware neural architecture search. The goal is to find a good compact model with neural architecture search. So neural architecture search, the main idea is to convert a design problem into a search problem. As a design problem, you have many design choices. And as humans, you usually try some of the design choices and see which one is better, and you keep them, and you iterate, and so on. But when we leverage the compute, we can turn it into a simple search problem. So it basically works in this way. You first design a search space, and in the search space, you put a lot of design choices into the search space. And then you leverage some search algorithm. Those search algorithms can be, there are a lot of search algorithms in optimization domain. You can use RL, evolution, and so on. And based on those search algorithms, and you try to find a good model in this search space. Well, how do you do that? Well, it's pretty simple. You can sample some models in this search space, and you train them on and measure some constraints like latency and accuracy, or maybe energy, flops, or parameters, and so on. And then you use the signal to feedback to this search algorithm, and this search algorithm can learn whether those sampled models are good or not. If they're good, you keep them. If they're bad, then you can drop them. And by doing this iteratively, you can find a better candidate in this search space. All right, so the first question is, how do we design a search space? A good search space is very critical for good performance. If there is no good candidate in this search space, then there is no chance you can find a good model, right? So in general, there are many ways to design search space. In the early work, or my teammate designed some search space. I call it a cell-based search space. It's mainly for NASDAQ and ImageNet. Basically, it follows the idea similar to Inception. You can design many placeholders, like each box is a placeholder. And in the placeholder, you can have many different candidates. They could be average pooling, they could be separable convolution, max pooling, and so on. And you also search for the connections between the input and those placeholders, and so on. So if you can see, this search space is radically new. However, it has a problem because the search space is huge. It has to restrict to a single cell. And then after you find a good cell, you will repeatedly stack the same cell. This is very similar to how human design networks, like ResNet, design ResNet block, and you stack them many times to become ResNet 50 or ResNet 100, and so on. However, if you consider efficiency, you will find those operations, their efficiency is actually depend on your input-output shape. And since we have the same cell across different network stages, they tend to be inefficient. So another way recently is quite popular is to do kind of, I call it layer-based. So essentially, if you look at the general convolutional neural networks, you will find it takes an input as image and has many layers, and those layers usually have stages, and they will do some downsampling or convolution and so on, and finally output the prediction for a certain number of classes. So this layer-based search space is to design a relatively smaller search space for each layer, but you allow different layers to have different structures. So essentially, you allow this kind of diversity across different layers. And inside each layer, Inside each layer, you can search some basic choice, like what should be the convolution, what should be the kernel size, how many times to repeat them, and what should be the channel size, and so on. So this layer-based search space is quite popular recently because they usually tends to have better efficiency and more flexibility. All right, let's say you already designed a search space. The next question is, how can we find a good candidate in this search space, right? Okay, my colleague actually used several optimizations that already proposed in previous work. For example, in the very early MNAS, we simply use reinforcement learning to search for a good candidate in the search space. The idea is like this. You know, in the network, you have many blocks. And inside each block, we can call them like placeholder. You have many candidates. Then you can formulate as a search problem in this way. Each placeholder could be a RNN unit. And this unit will output all the probability of different choice. For example, like this placeholder could be corresponding to this RNN unit. And let's say it has 4 candidates: separable convolution, average pooling, max pooling, and identity. Then this unit will output 4 probability. And the probability will indicate which op is a better choice for this unit or for this placeholder. And then similarly, you have many placeholders, so you have many RNN units. And finally, you can construct this RNN and use a reward. By reward, it means either it's accuracy or it's constrained accuracy. Use this reward to update those probability. After several iterations, you will learn like which choice for each placeholder is the best. And then you can sample the best candidate as a final search model. Similarly, our colleagues also propose a way to use evolution. This is relatively simple. The idea is giving this candidate or search space, you sample a batch of population and you train all of them. And then by training them, you know which candidate is good, which candidate is bad. Then you throw away those bad candidates and keep those candidates as a seed to sample another population. And you keep going until you converge to some good candidate. So anyway, using this search algorithm, we show like a NASDAQ and ImageNet, they have good trade-off between accuracy and flops and parameters than hand design models. However, there is a main problem for this RL-based or this evolution-based search algorithm is it requires a lot of compute. Usually, they may require like 10,000 GPU hours. For some cases, it might be acceptable, but for some people or some cases, it might be too expensive, right? You may worry, is it too expensive or I'm just too poor? I don't have enough GPUs, right? So to address this limitation, we also proposed a way called weight sharing to drastically reduce the search cost. As we can see in the previous RL-based or evolution-based, the main limitation is you need to sample a lot of candidates. And for each candidate, you will train them from scratch. Because you train them from scratch, you need to spend a lot of compute for each candidate. If you sample like tens of thousands of candidates, then your computation cost is too high. The weight sharing, it takes another way. It based on assumption that if you sample some candidate, you train them, then you can keep those weight for the next generation. So when you sample the next batch, you can just reuse the weight that is already trained in the previous batch. So in order to do that, it constructs a supernet. This supernet will contain all the design choices of your search space. And each time, you just sample a subpath. Like for example, you sample this path, and you as a candidate and you train this candidate. After you train it, you keep this weight. Next time you sample another pass like this, because some of the weights, they are already trained in the previous pass. So if you sample a new pass, the training could be very fast. It could be a couple of steps or even a single step. So by doing this, you can see you can sample a lot of candidates, but each candidate only train a couple of steps instead of like thousands of steps. So in this way, it can significantly reduce the cost. Usually, it reduces the cost by like 100 times or even 1,000 times. And there are many new work like DARS, our proxyless NAS, FBNet, and our new TUNAS work. They're all based on this idea. However, this weight sharing is also not ideal. As you can see, because you reuse the weight trained in the previous candidate, there could be some bias. For example, if you train one pass very often in the early stage, then those weights tends to be well trained. And if you sample a new pass, and this new pass is not well trained, they may perform less good, worse than the originally heavily trained pass. And then the controller tends to keep sampling the same pass and so on. So in summary, this weight sharing can reduce the computation cost, but there are also still some issues like bias and so on, which needs to be addressed. So that's kind of a new research topic recently. Many people are trying to address. So now you already have a search space and you have a search algorithm and you can find a good candidate. But this is how our NASNet and ImageNet we did. But in production and in reality, and many times you not only care about your accuracy, you also care about some other constraints like latency or flops or parameters and so on. So the question is, how can we incorporate those constraints into your search process so the controller can find a good candidate that not only have good accuracy, but also have good latency or parameters or flops and those constraints? It turns out we did a lot of study to see which way is best, but it turns out a very simple weighted product or weighted sum is good enough to approximate your operator optimal solutions. Like a simple way is like this. You can just do a product between your accuracy, ACC, and your latency constraint. Of course, you need some hyperparameters like W to balance the trade-off between your accuracy and latency. If you care more about accuracy, then you can lower the weight of its latency. If you care more about latency, then you can increase the weight of this latency. And here we showed two examples of how to set those constraints. On the left part, we can set the latency constraint as a hard constraint. Let's say your constraint is 75 milliseconds like this. And if you do a hard constraint, which means if your candidate has a latency longer than your constraint, then you don't want to keep this candidate. So in this way, the controller tends to sample a lot of candidates that is below this latency constraint. So they can make sure the final network can satisfy your latency constraint. You can also treat it as a soft constraint. By soft constraint, it means, let's say your target latency is 75 milliseconds, but your actual latency, it could be higher, it could be longer, as long as you have much better accuracy. So in this way, the controller tends to sample a wide range of models that could be longer than the target latency or could be faster than the target latency, but they tend to try to find a better trade-off between accuracy and latency. So putting all of them together, like the search space or controller search algorithm and constraints and so on. Here is the example. We based on MobileNet v2, but we make some of the design as a configurable. For example, some of the convolution, some of the blocks that originally could be 3x3 kernel, then we can make them configurable. It could be 3x3 or 5x5 or even others. And similarly, for expansion ratio, the default could be 6. Then we could make it configurable like a 3 or 6 or so on. Then you put all these options into the search space and ask the controller to find a good candidate in this search space. And interestingly, this controller actually found some quite different things than human design networks. For example, it used a lot of 5x5 depth size convolution. And before this work, actually, there's no one use 5x5 depth size convolution in mobile size models. But this controller turns out it figured out like 5x5 depth size convolution is actually helpful. And later work even find like a 7x7 could be also helpful. Another thing is, if you look at this network, there are many layers, and these layers actually have different structures. Some of them, they are 5x5, some of them, they're 3x3, some of them, they are MBCom3 or MBCom6. So diversity is important, or figured out by these controller algorithms. So these results are summarized on ImageNet using AutoML. We start from MobileNet v2, and then we do some search to get better accuracy. We call it MNASnet. And later on top of MNASnet, we also did some extra optimizations, like we change SE, we add the H switch, we apply net adapt and compact layers and so on to further optimize it. So one of the additional lessons learned from this MobileNet v3 is that this AutoML design or neural architecture search design, it can be complement with human design, because AutoML design, they can only try to find a good candidate in the search space. And this search space is designed by human. So it's limited by how good is your search space. In the contrast, human is very good at intuitions. We can come out some new design choices that is never learned or never thought about before. Just like MobileNet v3, even the MNASnet is already searched by AutoML, but on top of that, we add some human intuitions and optimizations to further optimize it. So another thing I want to highlight is NAS could be a good tool. Sometimes if you come out some new building blocks or new optimizers or some new things that could have many design choices, and as a human, it is very difficult to pick the best design choice. In this case, you can leverage NAS to help you find the better design choices. So with my colleague, we did a simple study for MixNet. The idea is we find you can usually each layer only have one kernel size, but we find if you mix those kernel size like 3x3, 5x5, and k/k, then they will be help the accuracy. This idea is actually already used in Inception and other networks. However, the question here is, if you have many different kernel size and you need to divide those channels in different groups, then as a human, it is very difficult to figure out the best design choice for each layer. Let's say you have 3 groups or 4 groups, and you have 20 or 50 layers, then the design choice could be huge. Design space could be huge, right? Well, here we can put those as a design choice and convert them into a search space, and then ask NAS to figure out the best design choice for each layer. And by doing this, we come out this new network called MixNet. The search space is very similar, pretty much the same as MNASnet, except we add this new building block into the search space. As we can see, after you add this, it has this new searched results. Even though they're using the same search algorithm and very similar search space, their accuracy is much better. So in summary, so in many cases, you can just use MNAS as a tool to help you figure out the best design choices. All right, so far so good. All right, on mobile side, it looks like we have designed pretty good models in terms of latency and accuracy. However, if you look at the big picture, this small dot is our previous model, like either MNAS or MobileNet v3 or MixNet and so on. They still have a huge accuracy gap between the state-of-the-art models, right? So definitely we are not satisfied. We, as an AutoML or research, we not only wanted to design small compact model, we also wanted to design better high accuracy state-of-the-art models, right? So how can we do that? Well, a simple intuition is you can design a super huge search space and then apply the same search algorithm and try to search for a better model in this huge search space. But unfortunately, they are either constrained by the compute resources or by the limited some limitations in the weight sharing algorithms. So in 2019, we come out some other ways. So we ask, can we take those compact model and somehow to scale them up in automatically or in a unified way to get higher accuracy model? So this idea leads to our next work called EfficientNet or EfficientDet. So in order to understand how we scale up models, let's first look at how people usually scale up convolutional neural networks before. So giving this baseline, there are many ways to scale up a model. The first way is you can add more channels to make it wide. The second way is you can add more layers to make it deeper. And the third way is you can also increase the image size to make the resolution higher. And usually, most of the previous networks take one of them. For example, MobileNet, mostly we use depth multiply to scale down the width. And the ResNet usually will scale up the model by adding more layers to make them deeper. So we did some study. We take a baseline model and scale up, try the different ways to scale them up. And the left part is to make them wider. The middle part make them deeper, and the right part is to increase the image resolution. It turns out the accuracy actually pretty saturate pretty quickly. So we can only reach like 80 or 81% accuracy. So we're thinking like why they're limited by they saturate so fast, and what is the limitation? It turns out the limitation is we only scale up one dimension, which if you scale up one dimension, then you will limit it by another dimension. So the solution is pretty simple. You need to scale them up all together. So you need to scale up everything, basically. Based on this idea, we propose this compound scaling. Giving a baseline, you can scale up all these different dimensions simultaneously to make them deeper, wider, and higher resolution. So what is the intuition? Why do we need to do that? Well, it's pretty simple. To give you an example, for example, when you increase the image size or increase the resolution, then the original layer will see a much smaller area, right? In another way, the receptive field will be not enough to capture the larger image size. So in order to address this issue, you need to add more layers to increase the receptive field. So you need to make them deeper. Similarly, if your image size is bigger, then you will have more details. And we know more patterns, and we know each channel is trying to remember some kind of patterns. And if you have more patterns, then you need more channels to capture all those patterns. So now the problem is now you have 3 dimensions like depth, width, and resolution. And let's say you want to make the model 100 times bigger, but you have 3 dimensions. How can you know what is the scaling factor for each dimension, right? A simple way is, let's say you want to scale to 100 times bigger, then you can do a grid search for all these dimensions. But the problem is, if your model is huge, then doing this search will be very expensive. And we find there are actually invariant or inherent correlation between those different dimensions. We use this, we reformulate this scaling problem using 4 additional parameters, alpha, beta, gamma, and phi. And we constrain alpha, beta, gamma in this way, such that after you scaling, regardless what is the value of alpha, beta, gamma, your model size will only depends on the single factor phi, because their products is a constant too. So your total compute after you scale will be 2 to the phi. So now the problem is, now you have this constraint for these 3 alpha, beta, gamma. How do you know the correlation between these 3? Well, it's pretty simple. It turns out you can do it in 2 ways. First, you can fix phi, and you want to scale to fix the size. Let's say phi equals 2, and you want to make the model 4 times bigger. Then, because the model is relatively small, you can do a local search, grid search, to find the value of alpha, beta, gamma. Then you fix alpha, beta, gamma, and only scale phi to get different target resources. So we tried this compound scaling on MobileNet V1, V2, and ResNet 50, and it turns out they all improved accuracy on the target constraint, resource constraint. As a comparison, we take the same model as a baseline model. We scale up this baseline model using different ways. One, the bottom 3 lines is scale up by single dimension, either width or depth or resolution. And the top line is to scale up by this compound scaling, scale up all these dimensions. It turns out like doing this compound scaling can achieve much better accuracy than you scale up a single dimension. So putting all these things together like a single model, this is found by the MNAS, and doing this compound scaling, as we mentioned before, this new EfficientNet model is actually better than the previous MNAS, NASNet, AmoebaNet, and other ResNet, and so on. Of course, we also tested the transfer learning performance on CIFAR and other small dataset. It turns out they also perform pretty good. And lastly, we also tried this for object detection. We put using this EfficientNet as a backbone and scale up this BiFPN using some kind of compound scaling. And it turns out, even for object detection, this EfficientDet, it starts from this D0 and scale up using compound scaling. This scale-up model has much better trade-off between accuracy and flops and latency than the other previous models. And for segmentation, it is similar compared to DeepLab, AutoDeepLab, or Panoptic DeepLab. Our scaled model has a much better trade-off between accuracy and flops. All right, so this is the main topic of my talk. We still have 5 minutes. I can introduce a little bit about some other wide topics. The first topic is, how about hyperparameters? You know, in the previous neural architecture search, we're trying to find a good architecture. However, in reality, after you find the neural architecture, or before you find the neural architecture, you need to determine what are the best hyperparameters, like learning rate, weight decay, optimizer, and so on, right? You don't simply pick a random hyperparameter. Well, we ask, can we also automate the hyperparameter design choice. Well, it turns out this is also doable. This is a recent work I did with my colleagues. It's called AutoHAS. The main idea is to incorporate this hyperparameter into the MNAS framework. So in that case, you can jointly search for neural network and hyperparameters. We did some study using this AutoHAS compared to other random search or Bayesian optimizations. This AutoHAS can actually find a pretty good accuracy model, but using much less computation cost. Here we also use weight sharing to reduce resource. And on some data sets like ImageNet, CIFAR, or Flowers, we tend to also improve their accuracy by a reasonable margin. For ImageNet, the accuracy again is limited. I guess one of the reasons is ImageNet is usually well-studied, well-tuned by a lot of researchers. But for some other data sets like Flowers, which is less heavily tuned, in this case, by tuning these hyperparameters, we can get much better accuracy, like 11% accuracy gain. All right, the last topic is recently quite hot, is about training efficiency. You know, EfficientNet, when we propose this, it's mainly for inference, like flops, parameters, and so on. And recently, a bunch of works have been proposed trying to speed up the training as well. Well, so we ask, can we also leverage neural architecture search to improve your training speed? This is a work in progress work. It turns out by leverage this training MNAS, we can significantly speed up your training and get better accuracy. All right, that's pretty much my talk.
Thank you, Mingxing. Fantastic talk. Thank you so much. Please, everyone in the audience, please put your questions into the QA. I can see we already have some, so keep adding the questions. I can see someone's put questions into the chat. Don't do that. Put it into the QA, and that way we can work with them. So I have a question here from Alok. Alok, if you want to ask your question yourself, please raise your hand, and then I'm going to unmute you. I think it's better if you ask your question yourself. I think generally, if people want to ask their questions themselves, then I think it's better, and we're more likely to select those questions that people have their hands up. So, Alok, could you put your hand up if you'd like to ask your question? If you really, really don't want to, then I'm going to ask it for you, but I'd much prefer that people ask their own questions. Okay, Alok, you don't have your hand up, so I'm going to ask it for you. Can the search space be expanded to include alternate network architectures such as attention-based vision transformers and upcoming GLOM hierarchical-based ones?
Good question. So this vision transformer is very new, and we are actively trying to come out some better vision transformers. And there are some challenges, but it's still doable, and we can make some progress. Like some of the challenges is transformer is actually pretty simple compared to convolution. Transformer has all these layers, the same layers. So you don't, the design choices for vision transformer is limited compared to convolution. But you can definitely add more design choices, and for example, you can consider what should be the number of heads, what should be the channel size, what should be the sequence length, and so on. You can put all of them into the search space, and then the controller will try to come out with better design choices.
Okay, thank you. Oh, I should invite Giuseppe and Alessio into the discussion. Sorry, guys. Do you guys have any questions you want to ask?
Yeah, so you touched a bit already about it already in your talk, but how much do you think the design of the search space influences this? And I want to ask you if there is a way in that the human design that is put in the search space somehow constrains this method? And if so, what can we do to improve this?
That's a good question. Yeah. So as I said, the search space is very important. In my opinion, is underexplored in research. I know a lot of papers trying to come out a better search algorithm, but in terms of search space, not many research are on this. However, the search space will largely constrain the performance of your final networks. And so far, all the search space is manually designed. And so they are definitely limited. But I would say there could be two ways going forward. One is, as I said, you can treat the MNAS or AutoML as a tool. So there could be some iterations. For example, you using the current knowledge, you design a good search space, you come out some better model. It could help human to get some more intuitions, right? You get some more intuition. You may come out some new building blocks, and then you can put back into the search space and do another search and to get a even better. So you can do it kind of iteratively. That's one way, but they're still limited. Another way, it might be a little bit more dramatic, is AutoML 0. My colleague, they are working on this. The idea is you design a super huge search space. They don't even have backpropagation. They don't have any, so many of them, they're customized. Even for humans, you don't inject much human intuition. You just put all the things into the search space. And then using this huge search space, it may come out some better optimizer or better or activation functions, or even something similar to backpropagation. But it's still limited by the compute. If your search space is huge, including everything, then you can only focus on small data set and a small network. But these days, the state-of-the-art models, they're huge. It's not realistic to design a super huge search space for those big models.
Right. See, thank you.
Yeah.
Okay.
Thank you.
I see we have a couple of people with their hands up. So, Chris, if you could put your question into the QA first, we're going to call on you. First of all, we're going to go with Elko. So I'm going to allow you to talk, Elko. Go ahead.
Thank you. Can you hear me okay?
Yeah.
Yep.
Great. So I was just, my question was, can you elaborate on why you separate the super network path search and the scaling up? So just to kind of clarify, it seemed like you had this first stage where you had a super network where you were using a controller to find a path.
Yes.
And then you then scaled up that core network afterwards. But could you do it all in one go just by having lots of like layers that could be identity? And
good question. Thank you. Yeah. This is definitely a very intuitive idea. Why don't you construct a super big supernet, and then in the supernet you can find some good candidate for large models as well. However, as I said, there are some limitations on weight sharing or supernet. Like if your model is super big, one problem is because your supernet contains all these design choices, they usually require much more memory and much more compute. So if your model is very big, you will likely run out of memory. But there are some ways to mitigate this as well. There is also another issue, as I mentioned, is there are some bias in the weight sharing, like supernet-based weight sharing method. We did some study, and we are trying hard to make it work. But so far, there are still many issues to resolve. And many times, the controller tends to find some model in this big supernet, but those models are not as good as expected. So I would say going forward in the future, this should be the right way. But right now, in the current stage, there are several limitations or or challenges we need to address in order to achieve that goal.
Great, thank you. And thank you for the talk. It was very interesting.
Thank you.
Thanks for the question, Ilko. Okay, I had a quick question. So Mingxing, for EfficientDet object detection, how much, I guess when you include the whole system, like pre-processing and MNAS, non-maximal suppression, how much room for more improvement is there on optimizing the middle bit of the whole process, which is finding the bounding boxes and doing the regressions? And a kind of a follow-on question to that is, what's the future there? Do you think that some, like there are methods like transformer-based methods which don't need to have an NMS step at all?
Yeah,
do you think
got
that
you.
in the future, or where do you think that things are going?
Yeah, this is a very interesting topic, especially since DETR and this new VIT. It's definitely a very interesting and new domain. Like, what if we don't have an MS? Conventional object detection, like EfficientNet or RetinaNet, they're very complicated. There are many post-processing. And this new transformer seems very promising to completely get rid of that. However, there are also some challenges that require a lot of further research in the future. For example, on object detection, there is a common practice is to use very large images, because object detection is not a classification. You need to detect many small objects. And right now, a lot of people using the vanilla transformer, the attention part is kind of square. The complexity is square to the number of pixels. So if your image size is big, then it tends to be very expensive. I actually played with DETR as well. And I find like for smaller images, DETR is actually reasonably good. But for bigger images, they have some troubles to identify those objects. But those big images, is very critical for real applications like self-driving cars. They're usually high resolution, and those objects are very small. But I would say there also could be some ways like a linear transformer and others. I honestly, I don't know which one is the best, but if you want me to guess, I would guess maybe this kind of hybrid will be the best. But get rid of those NMS and post-processing is definitely the right thing to do.
Thank you.
Yeah.
Okay. Alessio, do you have another question, or should we go to the audience?
Yeah, so I wanted to ask, like you mentioned at the end, towards the end of the talk, that there have been new models that try to tackle the training bit. So there's been a lot of improvement in efficiency of the architecture, but what about the training? Because even for efficient architectures, these take a long time. So how much do you think there can be done here? Because like even EfficientDet, it takes many TPU days to train, and not a lot of people have that kind of computation. Yeah, so I want if you can elaborate on that a bit more, because I think it's very interesting.
Yeah, definitely. So this is I overlooked on this part on the training efficiency before, because I know in real world applications, a lot of people will spend quite a lot of resource on inference, because after you train the model, you will deploy this model. However, training these models is also non-trivial, especially for detection. And these image sizes are huge and take a lot of devices compute. So recently, we are trying to speed up this training efficiency. It turns out we played a couple of factors to speed up your training. One is image size plays an important role in training efficiency, because image size will impact your activation and impact your memory and impact your batch size and your training efficiency, and so on. So that's one critical point. Another is some regularization is also important. If you have more regularization, you definitely need to train longer. Like EfficientDet, we actually train a lot of epochs. If you want to train faster, you may need to use a different training strategy, like optimizers, regularizations, and so on. So we did some study for ImageNet, at least. If you are properly use a good image size and also a good regularization, then you can significantly speed up your training as well. We hope like later on we can spend some more time for object detection as well, so people can easily train these models as well.
Okay, thank you very much.
Thank you.
Okay, question from Sean. Sean, stick your hand up. We're pressing raise hand if you want to ask your question. I was going to ask it for you. Oh, sure, great. Fantastic. Go ahead.
Hey, well, first of all, thanks for the talk. It was very interesting. I was interested in the weight sharing and how that was actually implemented in code. Does it make the code very complex, or is there? It seems like it would be quite difficult with, say, PyTorch or TensorFlow to implement that kind of thing. Or do you have any examples online where I could see this weight sharing being implemented, or how did you find it?
Thank you. Yeah. Yes. This weight sharing is a little bit more complicated than your multi-trial search, because multi-trial, each model is just trained from scratch. Here you need to construct a supernet. However, like using there are both open source code for PyTorch and TensorFlow. For PyTorch, I would recommend you can look at these DARTs, DARTs. This is quite popular in PyTorch. If you want to look at the TensorFlow, we have a recent work called TUNAS, TUNAS. It's in open source in Google Research. You can take a look. Maybe I can tap here.
Thank you.
Cool. MNAS, I think you had your hand up. Oh, your hand's up. No. MNAS, so we're going to ask you a question, but I think you had your hand up. It's gone away now. Oh, there you go. Great. Go ahead.
Hi, very nice talk. I just wanted to ask if you have investigated different type of objectives, such as related to robustness, and if you approach that through your research on training methods, or because before you said that you were trying to optimize for accuracy and compute time, but
yes.
For example, in computer vision for self-driving cars, also robustness, and it's very important.
Yes. Very good question. Very good question. Thank you for proposing this. Like last year, I actually spent some time with my intern, Zihang. We're trying to investigate, can we use NAS to find a model that has better accuracy and adversarial robustness? There are several issues. We got some promising results, but there are several issues. One issue is adversarial robustness is kind of expensive to train because it needs to use adversarial training, and you need to do this backpropagation multiple times. And this increases the computation cost to do this joint search for accuracy and adversarial robustness. This is one of the issues. Another issue is there could be many reasons, but in our experiments, we didn't find much better or much different structures that can benefit a lot on adversarial robustness. I guess one of the reasons is as I said, is constrained by the search space. For robustness, you might need different building blocks or different things that can benefit this robustness. So for example, recently we find activation is actually important for robustness, like smooth activation and so on. But at that time, when we designed this search space, we didn't incorporate those things in the search space. That might be one of the reasons that we miss some of the potential gains by using NAS to finite robustness. But I would say this NAS framework is actually pretty flexible. Right now, we optimize accuracy and inference latency or flops, but you can simply replace the inference metrics with robustness and do another search.
Okay, thank you very much. Very interesting.
Yes, thank you.
Thanks, MNAS. We have a question from Max. Max, raise your hand if you can. No. Okay, I'm going to ask Max's question. Max asks, is there work that maximizes data efficiency for data-limited domains? It will be interesting to see how optimal a network architecture varies with dataset size.
This is an interesting question. By data efficiency, you mean you can use less labeled data, or do you use like less just any unlabeled data? I guess it's less labeled data, right?
I think so, yeah.
Yeah. So in this case, we haven't explored, and I haven't thought about this, but it's a very good question. I think one of the questions is, let's say you have two data sets. One is big data set, another is a small data set. Do you need to specifically design a network that for the small data set? That's an open question. I'm not sure. But at least my colleague a few years ago, maybe 2 years ago, they have a paper called "Do Better ImageNet Transfer Better." They did a study on transfer learning. It turns out if you have good architecture that perform good on ImageNet, it's relatively big data set, then you will have more chance, most likely, you will also perform pretty good on those small data set like CFAR, bird, cars, and so on. So right now, most of the efforts we spend is on ImageNet or even bigger data set, because we based on assumption that if your model perform good on those data set, it probably will also perform good on small data set. But it's still open question whether we need to specifically search or design architecture for these small data sets or less labeled data, something like that.
Thank you, and thanks for the question. Okay, we've probably got time for maybe 1 or 2 questions. So just go to David Murphy. If you put your hand up quickly. Yeah, go ahead.
Can you hear me?
Yeah.
Yes.
Greetings, Mingxing. Thank you for the fascinating talk.
Thank you.
And the idea of performance measurement is strongly tied to the hardware and the scheduler for the hardware. So I'm wondering if you're aware of any work or consider work where one would ultimately search the hardware and scheduler space as well. And the output then is an architecture that's suited to your particular problem that you're trying to solve.
Thank you for the question. Yes, this is exactly what we are thinking. We actually recently released a paper is to jointly search for neural architecture and hardware architecture. And the results also thinking is kind of promising. Let me send you. Okay, I sent in the chat. This paper is called, yeah, it's called Rethinking Co-Design of Neural Architectures and Hardware Accelerators. We haven't looked into the scheduler, but we looked into the hardware design. Can we do a co-design of hardware and software? And it turns out if you do that, it's still early research work, but it shows some promising results. So the answer is yes, if you do this co-design, you can get better results.
Yeah, that's great, because then you can target, say, if you need a really low energy mobile device or you have plenty of power to spare, and you're just looking for the best speed. So thank you. Thank you.
Yeah. You're welcome.
Thanks for the question. So we've reached our time. Thanks so much, Mingxing. Fantastic talk.
Thank you.
Thanks for the interesting discussion as well. Thanks to the audience. We're going to be uploading the video, and all of the videos are uploaded to our YouTube channel. So please, please everyone subscribe or whatever it is you do on YouTube for connecting with us. You can connect with me on Twitter as well, at Martin Goodson. And I'm gonna let everyone know when the videos are going to be uploaded. So thanks once again, and see you next time. Thank you. Bye bye.
Thank you. Thanks everyone. Bye.